In section 7.1, we're going to discuss finding the area between two curves. So if you open your book to the first page in section 7.1, you'll see these three graphs. And it shows you exactly what we're trying to find here is the area between these two curves. Now, in terms of calculus, one way to think of this is that if you found the area underneath the curve of G between A and B, and then subtracted off that similar area for the curve of F, then the difference is going to be that region. That's fine, and that's essentially what we're going to be doing. Basically, it's going to be the integral of the difference of f of x minus g of x. But I'm going to set it up, or at least kind of give a different interpretation and approach to setting this up with the idea of what we're going to do in section 7.2. That is, work on volumes of solids of revolution. So what we're going to do kind of habitually in order to just set up that integral is this. We're going to look at the area of one little slice here of this region. Now this little slice can be approximated by a rectangle. And that rectangle has a thickness of delta x. What's another way to express delta x? What's something equivalent to delta x? dx. So delta x and dx. The area of this is going to be the height, which is going to be your f of x minus g of x, or actually, f of x minus g of x times its width. And if you add that up for all these possible rectangles, then you get an approximation to the area between these two curves. What you do next is take the limit of that sum as the width of these curves, or width of those intervals, gets really, really small. And in that limit, you're going to pass to the integral. So that's kind of a justification of how we get this. And we're going to use these ideas to set up our integrations. So we'll start with problem number 2, which is the area between these two curves. We have y equals 2x plus 5 and y equals x squared plus 2x plus 1. Now what I'm going to suggest that we do when we're trying to find these two areas is work with the area of one rectangle. So again, this is y equals 2x plus 5 and y equals x squared plus 2x plus 1. So we want to find the area of one rectangle. Area of one rectangle. Well, the area of a rectangle is just the height times the width equals the height times the width. The width is pretty easy. The width is going to be delta x, or better yet, what we're just going to use is dx. The height is a different matter. For the height, we're going to need the top minus the bottom. So what's that going to look like? Well, top minus bottom times dx. The top function is this one right here. It's 2x plus 5. The bottom function is this one here, x squared plus 2x plus 1. And then I have my dx. So the nice thing about this is that I've got this all in terms of x. I can do a little simplification here. If we subtract, let's see, the 2x's are going to cancel. And then what else? 5 minus 1 is going to be 4, so we'll end up with the integral. Excuse me, not the integral. I haven't got there yet. Just the area is going to be 4 minus x squared dx. So that's the area of one rectangle. If I want the area of all the rectangles, I'll add them up. And as this gets really, really small, we're going to pass from a sum to an integral. So we're going to integrate this. To add up all these possible rectangles, we're going to integrate. So let's see, that'll be the integral from something to something of 4 minus x squared dx. Now comes that important something. Where should I take those integrals? Over what interval? Remember trying to find this area. Go ahead, where was it from? Good. -2 to 2. And -2 is the farthest left in this region that you can take a slice. +2 is the farthest to the right you can take that slice. So those are the limits of our integral. -2 to 2. Does anything jump out at you about this integral? Not 0. But you're thinking along the right tracks. It's not an odd function, it's an even function. So reminder, if you have an integral from -a to a of an even function, good, it's twice the integral of the even function. But what happens to the limits? Oops. Good, 0 to a. All right, so it's not a big savings. I'm only pointing it out so that you get a little bit conditioned to looking for it. If you've got a symmetric interval, and by that I mean -a to a, look for these things. It helps out. So this is twice the integral from 0 to 2 of 4 minus x squared dx. Twice 0 to 2. Make sure you replace this with a straight line. Sometimes people forget to replace it with a straight line and then integrate again. You integrate once, you're done. What's the antiderivative of 4 minus x squared? Thank you. 4x minus x to the third over 3. So it's going to be 2 times 8 minus 8 thirds minus 0. So let's see. That'll be 24 thirds minus 8 thirds is 16 thirds times 2 is 32 thirds. Yay. So that's the area between these two curves. Looks reasonable. Should be a positive number when you're trying to find the area between two curves. How are we looking on that first one? Example 2. Yes? Well, the areas on both sides aren't necessarily going to be the same just by looking at it. But that doesn't matter. When we actually formed the integral, it's the integral that's an even function over a symmetric interval. So that's where we used it. But yeah, I mean, for me, looking at this going, gee, this area is going to be the same as this area, I wouldn't have been able to spot that. Yeah, so good question. Yeah, I didn't know that until we actually formed the integrand. Anything else on that one? Okay, let's try another one. Problem number 4. This time we're trying to find the area between these two curves, y equals x squared and y equals x cubed. Here's an interesting question for you. Which one's on top? Which one's the bigger function in the interval shown here? Is it the x squared or the x cubed? Well, if you actually pick a point and test it, suppose we chose, say, x equal 1/2. If I square 1/2, I get 1/4. If I cube 1/2, I get 1/8. So which one's going to be the taller of the two here? 1/4. So the top function here is your x squared. And you need to keep that straight. Which one's on the top? Which one's on the bottom? Y equals x squared. Y equals x cubed. So So we want to find the area between these two curves. What's the interval that we're going to be working with? Can anyone tell? 0 to 1. So 0 to 1 here. Now, as I did with the first one, I'm going to do with the second one. We're trying to find the area of one little rectangle. Now, it's not a big deal, but like I said, the purpose of this is to get you in the form and a habit for things we're doing later on. So, area of one rectangle. Area is going to be the height times the width, which is going to be top minus bottom times dx. What things should I put in here for top minus bottom? Thank you. X squared minus x cubed dx. Now this does actually have its place when I grade your exams. One of the things I'm going to be looking at when I grade your exams is, well, what integral did you set up? And in this case, this is your integrand. So that's, if you get that much, hey, that's 2-3 points of partial credit right there. Even if you screwed up everything else, you at least got a few points, right? So try and get these little pieces right. What am I going to integrate from? Well, we already went through that, right? 0 to 1, x squared minus x cubed dx. So x cubed over 3 minus x to the fourth over 4 between 0 and 1 is going to be 1/3 minus 1/4 minus 0, and that's going to be 1/12. So not necessarily with this one, but some of our other problems get a little bit lengthy, involved, etc. So sometimes on an exam, what I'll do is I'll say, all right, well, just set it up, and then finish it with a numerical integration. So let's practice that one time real quick here. Let's see that we get 1/12 when we do it with numerical integration. So you hit the math key, then number 9, the integral from 0 to 1 of x squared minus x raised to the third power dx. Now I'm probably going to get a decimal value, and then I'm going to have to hit the math key, answer the fraction. Perfect. Exactly 1/12. Really, really nice. If you're stuck with an old TI-83 or something like that, if you don't have the math type that allows you to type it into an integral, then what you would do is type in fn int x squared minus x cubed comma x comma 0 comma 1. So that's what you get, and you'll be able to get the fn int off of the math menu. Okay, let's move on to problem number 6. We've got y equals x minus 1, and our other function here is y equals x minus 1 cubed. Let me see if I can't pull this up on decimals for us, because there's something about this that I'd like you to see and note. So x minus 1 and x minus 1 cubed. Oops. Let's try that again. X minus 1 cubed. Let's see, this time we're going to go 0. Okay, so let's kind of zoom in here. What we're interested in is finding the area between these two curves here. Perfect. That's exactly the observation I was hoping you'd see, is that the top and bottom function change. So when you set up your integral, you're going to have to be very careful about how you do this. Let's just take a quick look at the beginnings of that work. So the area of one rectangle so as before, that's going to be top minus bottom times dx. So A equals top minus bottom times dx. But of course, as you pointed out, that matters, it matters on where you take your slice. So if I take my slice here, then what's going to happen? Well, the top function is going to be x minus 1, and the bottom function is going to be x minus 1 cubed. So it's going to be top, which is x minus 1, minus bottom, which is x minus 1 cubed dx. And that's going to help me out here in finding this area. Now, if you weren't careful in paying attention to the fact that the roles of top and bottom function changed, then you're going to get something very interesting happening with your area calculation. So if I just naively integrated x minus 1 minus x minus 1 cubed dx from, say, 0 to 2, so here's 0, here's 2. If I did that, then I'd end up with 0. Because what's going to happen is that by integrating these things with your top and bottom function mismatched, you're going to get a negative area here and a positive area here, and they're perfectly going to cancel each other out. So what should we do? 1 to 2? That only gives me half of my area then. Yeah, you could do from 0 to 1 and change the role of top and bottom function, and then add it to 1 to 2. Or how about if we just double this result? Now in this case, I'm not going to try and trick you with these things. These two areas are identical. If I do give you a problem similar to this, I'm not going to try and trick you by giving you areas that are similar, but they're not actually equal. All right. So sometimes, though, you will need to set up two integrals. You need to set up an integral from 0 to 1, and then another one from 1 to 2, or whatever the intervals happen to be. In this case, we'll just double the interval. Let me also make a small suggestion here. Is anyone really anxious to cube this out and integrate it? I mean, cubing that out is kind of a pain, even if you use tricks like Pascal's triangle or the binomial theorem, etc. It's kind of a pain. So here's a suggestion. Let's make a U-Substitution. Why not? Let's do this. What would you suggest I let U equal? X minus 1. And the cool thing is that du equals dx. So that's nice. And finally, let's change our limits of integration. So u at 1 is going to be 1 minus 1, which is 0. U at 2 is going to be 2 minus 1, which is 1. So nice. I'm going to change my limits of integration and be done with this in a snap. So this is going to be twice the integral from 0 to 1 of u minus u cubed du. And I'm done with the x's. Do not go back. Just finish it up here. It's going to be twice. Now I'll put that 2 on the left side of this, and on the right hand side I'll put the functions u squared over 2 minus u to the 4th over 4. So we end up with 2 times 1/2 minus 1/4 minus, well, when I put in the lower limit, I get 0. Overall, I think I end up with 1/2. Put yourself in my shoes for a second. What do you think the big point of this problem is from my perspective? What do you think I wanted you to see? I want you to see that these two changed their orders. Top and bottom functions changed. So that you have to be a little bit more careful when you set up the integration. There would have been nothing wrong with setting up 2 integrals to do this. In fact, in some cases, you have to do that. You're not always going to be quite so lucky to get a nice symmetric figure like this. But there's nothing wrong with taking advantage of it when you do. All right, how are we looking on that one? Okay? All right, good. Let's move on to problem number 18. And I'm sorry, we've outgrown our handout. I know, for a little while. We'll get back to it. There's more stuff we'll do on the handout. Somebody's Spanish stuff. Okay. Problem number 18. Y equals negative x cubed plus 2 and y equals x minus 3 between x equal negative 1 and 1. So this is problem number 18. Well, there's one challenge we face immediately, right? What's that? Yeah, we don't have the graph, right? So, you know, a couple ways to do this, but I would suggest that we use technology, right? Why not? So let's go to our graphing calculators. Let's enter in the two functions, negative x cubed plus 2 and x minus 3. As far as setting up your window is concerned, keep in mind that they gave you the limits for x, right? They told you it's going to be between negative 1 and 1. So set that up between negative 1 and 1, and then let your calculator do the rest. And what do I mean when I say that? Zoom 0. Good. Your calculator will then adjust the y coordinates. So I think I know which one's the top function, which one's the bottom function. Let me try and sketch that a little bit. So roughly speaking, we're trying to find the area between these two curves. Y equals negative x cubed plus 2 and y equals x minus 3. Not necessarily drawn to scale. Negative 1 to 1. As with all of these, we're trying to find the area of one little slice first. And I think you'll see a little bit more of the importance of this with some of the later problems in this section. It's not a bad way to go. Find the area of one slice. So that area is going to be the top minus bottom, which is minus x cubed plus 2 minus x minus 3 times dx. Top minus bottom. There is a little bit of simplification here. And it's nice to do this before we finish setting up our integral. So if I distribute the negative here and then collect like terms, I end up with negative x cubed plus x plus 5. Our limits of integration are, yeah, they're given to us, right? Negative 1 to 1. So the integral from negative 1 to 1 of negative x cubed plus x plus 5 dx. Yes, sir. You're right. It's minus x. Thank you. Now, there's nothing wrong with just integrating this straight ahead, but let's be a little bit clever. And by a little bit clever, this is what I mean. I'm going to split this up into the integral from negative 1 to 1 of negative x cubed minus x, thank you, Mr. Combs, plus the integral from negative 1 to 1 of 5 dx. Now, why did I do that? Can anyone suggest a reason? Yes. So here's your odd function rule, Gunnar. Negative 1 to 1. This is an odd function over symmetric interval. That's 0. So nice. Get rid of that right away. Over here, we don't even really have to integrate this one. Just think about what that is. That's this curve. Y equals 5. So y equals 5 between negative 1 and 1. Basically, you're trying to find this area. That's the area of a rectangle. Width of 2, height of 5. All right, so not drawn to scale very much, but that's 10. Nice. I'll try and make all your integrations this easy, okay? All right. Let's try problem number 24. Are we good with problem number 18? Problem 24. F of x is the cube root of x minus 1, and g of x is x minus 1. Now, they didn't give us any limits here, but presumably these two functions are going to enclose some area. So we have to figure that out. Probably a good way to approach this is to graph this on your graphing calculator. So as a quick reminder, where would I find the cube root function? I mean, you could write x minus 1 to the 1/3 power, but let's just, yeah, math. So hit the math key. Fourth option down is the cube root. We want the cube root of x minus 1. And then we also want x minus 1. One approach, since we don't know a good window, is the shotgun approach. You can just make everything go from negative 10 to 10 on both axes. I think we can probably zoom it down a little bit. Let's go from negative 4 to 4 on the x-axis and on the y-axis. And at least we should see where these two functions enclose an area. I think you can kind of already tell where it's going to be. So pretty similar to problem number 6. So we can kind of zoom in on our window if you want. We can make x min 0, x max of 2, y min of negative 1 to 1, And there's our graph. Why don't you see what you can do in terms of integrating this? So I think we have the setup. Let me write that down for us. The area of one rectangle. Actually, we don't quite have the setup. There's a little nuance we have to think about here. So let's change this function here. We want the cube root. Now, you know what? I'm just going to raise it to the 1/3 power. Be a quick fix on that. Raise to the 1 divided by 3 power. There you go. There's our quick fix. So we need to find the area of one rectangle here. See what you can do in terms of the setup. Not necessarily, although, I mean, there's going to be some for which you might not be given the graph, in which case you probably would want to graph it, you know, at least to see for yourself what's going on, unless you have a really good imagination for what these look like. Well, no, not the way I'm going to set it up. Okay, so there's two different ways to do it. What you have to keep in mind here is in problem 6 is that the top and bottom functions change at this point at x equal 1. So you can integrate from 0 to 1. In this case, the top function is x minus 1. The bottom function is your cubic or your cube root function. And then integrate from 1 to 2. Again, your top and bottom functions are going to change like this. So that's one way. There's nothing wrong with that. And a lot of times you're going to have to divide up your integral into intervals like this to account for different top and bottom functions. The other possibility is just to calculate one of these areas, say this one, integrate from 1 to 2, and then double the result. So 2 times this integral from 1 to 2 of the cube root of x minus 1 minus x minus 1. Now, when you do this, make sure that you get a positive result. If you made a mistake in your algebra or something like that, and you get a negative number, it's just wrong. And I don't have much sympathy if you get something that's clearly wrong and you don't fix it. Or at least write it, I know there's something wrong here, I can't find it. But if you get a negative number, that should be screaming out, there's something wrong. Please, try and find what went wrong. Now, for my part, in solving this the rest of the way, I'd probably do a U-substitution just to make my life a little bit easier here. U equals x minus 1. du is dx. That's really nice when du equals dx. That means our work in here finishing is going to be pretty easy. U of 1 would be 0. U of 2 would be 1. So this becomes twice the integral from 0 to 1 of, that'd be u to the 1/3 power minus u du, or 2 times 0 to 1 of, let's see, it's going to be 3/4 of u to the 4/3 minus u squared over 2. Okay, looks good. Twice. Plugging in a 1 here, I'm going to get 3/4 minus 1/2. Plugging in a 0, both of those are going to give me a 0. I end up with 1/2. Any thoughts on problem number 24 here? How are we looking on those? How are we looking on this one? Let's go back to our handout. We're going to find the area between these two curves. X equals 9 minus y squared and x equals y minus 3. So there's a little bit of a difference here. Suppose that we're trying to find this area and you think of taking some slices. Say here, take a slice. And it works out okay. You take your dx slice, you got a top minus bottom function, and we can use that to integrate in the interval from 0, excuse me, from -7 to 0. And that works okay. But what's going to happen when we go from here to here? Then it gets a little bit trickier. You don't have separate top and bottom functions here, do you? It's just from a function to itself. Now, in this case, there is something you could do, but you're really going to start working hard if you try and do this one with a dx slice. You're going to have to set up two integrals, and then over here, you're going to have to realize that, oh, gee, all I need to do is double the area from 0 to the function, and then work it that way. It's a lot of work. what you need to consider sometimes is taking a different approach. So, same two functions, but what kind of a slice am I taking now? This time I'm taking a dy slice. And the nice thing is that the right-hand function and the left-hand function don't change throughout my problem. So if I took a different slice at a different height, say up here, the right and left-hand functions don't change. So here to here, and then this one. That's a dy slice. I could take a dy slice down here. The right and left-hand functions do not change. So let's set about a familiar problem then, and that is find the area of one rectangle. The difference between this and the last one is that our calculation of the area is going to be a little bit different. When we were taking a dx slice, the height of our rectangle was the top minus the bottom. This time I'm going to need to characterize the width. The height here is just going to be dy. So the area is going to equal the rightmost function minus the leftmost function times its new height, which is dy. In this particular case, the rightmost function is the parabola, so it's going to be 9 minus y squared minus the leftmost function, which is going to be y minus 3. If I distribute and then collect like terms, let's see, what will I get? I'll end up with a minus y squared and then a minus y and a plus 12. So that's the area of one rectangle. That's your integrand. That's 3 points right there, if you can get that set up correctly. I need to add up the area of all such possible rectangles, starting from down here all the way up to here. And when I do that and let these things get really, really small, effectively what I'm doing is I'm integrating. So I'm going to integrate negative y squared minus y plus 12 dy. What should my limits of integration be? Well, keep in mind that I'm integrating with respect to y. So what's this point down here? Negative 4. What's this point up here? 3. So my integration should be from negative 4 to 3. Now, there's nothing wrong with me making your life a little easier on the test and saying, okay, set it up, but finish it with fn int. So if you want to take time to practice that, it's not a bad idea. Can I just give you the happy ending here? All right. 57 and 1/6 would be the happy ending. But what if you didn't have a nice graph like this? What if you're like, gee, you know, my TI, it can't graph this. I need to have y solved for in order to graph this. And with at least part of this, it'd be at least a part of a problem. And you know, this one you could work out pretty easily, but gosh, you know, I don't know how I'm going to find these things in general. In general, what you're going to have to do is set up an equation. I want to know where these two things meet. So to do that, you could solve. You could set them equal to each other. You could say 9 minus y squared equals y minus 3. I'll move everything to the right-hand side. So that's going to become a y squared. I'll subtract 9. So negative 3 minus 9 is negative 12. And this is a quadratic equation now. So it's going to be 0 equals y plus 4 times y minus 3. And I sincerely hope that you can read off the solutions here of -4 and +3. So sometimes you're going to actually need to solve for those points of intersection. They're not going to be given to you. Any thoughts on this one? Let's try problem number 26. Bottom left of my file cabinet, I need some more scrap paper. Thanks. Problem 26. F of y equals y times 2 minus y, and g of y equals -y. So these are two functions. We want to find the area between these two things. Boy, it starts out tough. We don't even have a graph on our handout. What are we supposed to do? Panic. Can I text a friend? All right. Well, let's keep in mind that f of y is really interchangeable with x, and g of y is also interchangeable with x. So we've got these two functions. Now this one, you could just solve for y, get y equals -x, and you know what the graph of that looks like, I hope. It's just a line that divides the fourth and second quadrants. But this one, well, let me distribute that. Yeah, I'm going to write it as -y squared plus 2y. Same thing, though. But what's the basic shape of this? Can anyone tell me basically what's it going to look like? A parabola, right? A parabola. Now let's think about this parabola a little bit. One of the things we can look at when we're looking at a parabola is the y-intercepts. How do you find the y-intercepts? Good. Set x equals 0. Okay, so let's do that. If I set x equals 0, y times 2 minus y equals 0. Well, can you read off the possibilities here? So that's where this graph is going to cross the y-axis. We also know something else about this. Because that coefficient of y squared is negative, which way is this going to open? To the right or to the left? Thank you. Opens left. So it's going to open to the left, and it's got y-intercepts at 0 and 2. So, perfect. Let's draw that. So, now this isn't necessarily supposed to be really wonderfully accurate or anything like that. So here's 0, here's 2, opens to the left. And then we remember that we have this function here, which is x equals -y. Fortunately for us, that graph encloses a region. We could try and find the area of that region between those two curves. Can I do this with a dx slice? Should I be taking a slice vertically? That'd be a lot of work. Because right here, your slice is going to go from a function to the same function. And unlike the last problem, it's going to be really nightmarish to try and characterize this part of the curve different from this part of the curve. It's just going to be a lot of work for you. So we'll take a dx or a dy slice. The nice thing about a dy slice is that the right and left functions don't change. It's just the same throughout the interval. So from here to here, find the area of one rectangle. So see if you can't come up with an expression for that. The second curve here is y equals, x equals y times 2 minus y. So the rightmost function, let me rewrite this as negative y squared plus 2y minus the leftmost function, which is negative y, gives me negative y squared plus 3y dy. But, I don't know, 0 to 2? Yeah, it's going to go higher than 2, right? Because this area, the area that's trapped between these two curves, extends in the y direction higher than 2. Now, a couple of people already figured out where it extends to. It extends to 3. Now, how'd you get 3? Good guess, or did you? Beautiful. So if we take these two curves, negative y squared plus 2y equals negative y, and set them equal to each other, I'll add y to both sides, factor out the minus y, and you can see your two solutions, y equals 0 or y equals 3. So those are your limits of integration. So the last step here is to integrate from 0 to 3 of negative y squared plus 3y dy. There's lots of little points that you can get along the way. Even if you get the final answer wrong, getting the right limits of integration, those are a couple points. Getting the right integrand, those are a couple more points. And then finishing it off correctly, again, a couple more points. All right. Do we need to go through the integration here? Thank you. 9/2. Right. If you did it on your graphing calculator, it would probably come out as 4.5. Let's look at problem number 38. F of x is sine of x. G of x is cosine of 2x. And they tell you up front that you're going to look at the values of x, or the area between these two curves, between negative pi over 2 and pi over 6. I guess one thing that remains to be seen then is, all right, well, what's the top function, what's the bottom function? Tough to tell with these trigonometric functions, especially the second one, the cosine. It's like, well, I don't know, cosine of 2x, you're decreasing the period. The period here is half of what it usually is. It's pi instead of 2 pi, but what's it look like? So let's do it this way this time. I'm just going to go over to Desmos and look at it there. So f of x this time is going to be sine of x, and then g of x is going to be cosine of 2x. Well, I need to change my limits of integration here. Limits of integration are going to go from negative pi over 2 to what was it? Pi over 6. You know, I think I need this one to be the pi over 6. Pi over 6. 6. Okay. So let's see. Where'd that one go? It didn't change. Try it again. Negative pi over 2. Step by. Okay, so there's one, and there's the other. Minus pi over 2 and pi over 6. Minus pi over 2 and pi over 6. How come it's not giving me that one? It's not giving me the top one. In any case, here's our two functions. Which one's here? Which one? Is this the cosine or is this the sine? Cosine. Yeah, the cosine is the top one. So it's pretty much what we needed from this. Now, if you're stuck graphing this on your graphing calculator, you can still get this. You can still find the top and bottom functions. What I suggest is you use different colors for the different curves or different styles. But back to the actual integration, we're going to integrate from negative pi over 2 to pi over 6 of sine of x. All right, try again. Cosine of 2x minus sine of x dx. Now, one of these isn't too bad. First thing first, it's not a symmetric interval. You're not going to be able to use your even properties or your odd properties. There's no real shortcuts here. Sorry. We are going to have to fiddle with this a little bit. So let me break this up. Negative pi over 2 to pi over 6 of cosine of 2x dx minus integral from negative pi over 2 to pi over 6 of sine of x dx. Why do you think I split this up like this? Anyone? We can integrate this one, right? What's the integral of sine of x? Negative cosine, good. So negative cosine of x. But this one we don't have a nice antiderivative, right? This isn't a basic form yet. You know, unless you're really good with the mental arithmetic, you kind of have to make a U-substitution. So we're going to let u equal what? 2x du equals 2 dx, so 1/2 du equals dx. So you're kind of stuck on this one. If u equals 2x, then we can do u of negative pi over 2. Negative pi over 2. So twice that's going to be negative pi. U of pi over 6 is going to be pi over 3. So the reason I split it up is because that second one, I've got to figure it out using a U-substitution. My new integral is the integral from negative pi to pi over 3 of the cosine of u times 1/2 du. You can factor that 1/2 out in front, doesn't matter. But now I need the integral of the cosine of u. Sine of u. Yeah, this is the nice one. 1/2 negative pi to pi over 3 of the sine of u. And let's see. The two minuses down here become a plus. Negative pi over 2 to pi over 6 of cosine of x. And let's keep going. 1/2 sine of pi over 3 minus sine of negative pi plus the cosine of pi over 6 minus cosine of pi over 2, negative pi over 2. Fortunately for us, a couple of these disappear. Which one of these terms disappears? Sine of negative pi disappears. Good, thank you. As well as cosine of negative pi over 2. Both of these are 0. What's the sine of pi over 3? Square root of 3 over 2. So this is going to be 1/2 times the square root of 3 over 2 plus square root of 3 over 2 again. If you factor out the square root of 3 over 2, you're left with 1/2 plus 1, which is 3/2. 3/2 times root 3 over 2 is going to be 3 root 3 over 4 for our final answer. Whew! All right. How are we looking with 38 here? Painful, painful. We're going to go back and cover this in a different way. I'm going to make it part of the next video, though. So, is there anything else on 38? If I wanted to graph this on my graphing calculator, so let's put those two functions in here. Sine of x and then cosine of 2x. Now they give us our limits of integration here, so I'll just go from negative pi over 2 to pi over 2. Oh, no, pi over 6, right? Pi over 6. And then hit zoom 0, zoom fit. And that'll perfectly fit the graph here. One thing you need to make sure of is that your calculator's in radian mode. If it wasn't, then these graphs would look all askew. They look pretty strange. Is that what you're looking for? Yeah. Okay, cool. Okay, let's stop things here. I'm going to do another video. It's going to talk a little bit more about the numerical integration part of this stuff.